6. And Chapter 6 sort of leads us into the remaining part of the course. It's really, in some ways, the gateway to the rest of our, well, really to the remaining 3/4 of organic chemistry. We've been laying a lot of groundwork now, talking about structure of molecules, understanding isomers and stereochemistry, getting a little bit of an introduction to the nomenclature and permutations of molecules, and talking about alkanes. And so now, as we go into the rest of the course, we're going to be doing a lot of discussion of functional groups and their reactivity. And remember, I said this was one of the biggies for organic chemistry. Chapter 6 is really the gateway to this, particularly in relationship to Chapters 7, Chapter 8. Chapters 7 and 8 deal with two types of reactions, substitution reactions and elimination reactions. And this is where organic chemistry really gets fun, because you start to learn how to interconvert molecules. You start to learn what turns a lot of people on to organic chemistry, and that is how to build molecules, organic synthesis. Chapter 6 begins talking about reactivity and how chemical reactions occur, with the idea of setting the groundwork for thinking about reaction mechanisms and all the processes that occur. And it ties into that second biggie we talked about, curved arrows. So to set the groundwork, we're going to, in Chapter 6, be talking about types of reactions, and we're not going to discuss every type of reaction, but we're going to set a little bit of the groundwork on two types of reactions, on substitution reactions and addition reactions, basically learning to make sense when you see an organic chemical equation of what's going on, literally how to read what's going on and how to understand it. We'll talk about the mechanisms in this chapter. Of reactions, particularly of substitution and elimination reactions, and this will set more of the groundwork for understanding things like the stereochemical course of elimination and substitution reactions. We'll also learn to think about reactions as overcoming energy barriers and going from reactants to intermediates and intermediates to products, or alternatively, from reactants directly to products. So, as I said, we'll be talking about the mechanisms and particularly the energetics involved. And part and parcel with energetics of reactions are the rates of reactions and a discussion of rate determining steps. And this is what we'll be getting over the course of this week. This is also the last week of the course where we very conveniently have the lecture in 1 week, discussion in the next week, and then a quiz in the following week to sort of bring it all home. This is where the quarter system gets us a little bit more compacted. So as we move into Chapter 7, and particularly Chapter 8, there's going to be even more burden on you to keep on top of things. So we'll be taking Chapter 7 up through Thanksgiving week, discussing that, including the week of Thanksgiving, discussing that in Thanksgiving week, and then having a quiz on it the following week, the very last week of class. And then the very last week of class, we'll be discussing Chapter 8, and you'll have that going on in both the lecture and the discussion, and then of course we move into the final in the following week. As I lamented before, I wish we had a little bit of an extra reading period to digest the last chapter of the class. All right, so let's take a look at one chemical reaction. I'm going to write it a couple of ways. Question. What's the next quiz going to be on? The next quiz is going to be on chapter 5 on Monday. So let's take a look at a particular reaction. We'll write it a couple of ways, and we'll use it and a few others as sort of springboards to talk about some of these points here about the types of reactions and the mechanisms of reactions, and later on energetic profiles. So let's take a look at the reaction of ethyl iodide, also called iodoethane, with sodium cyanide. Now I'm going to start to write this in various ways that you might see an organic chemist write things. One thing you probably will see is an organic chemist will often just focus on the organic product of the reaction. So you may see this reaction written like so, which would upset very much someone teaching general chemistry because it's not a balanced equation, and yet we're really organocentric here. We're of course talking about a reactant and another reactant going to an organic product. So people might even omit writing, write this in parentheses, sodium iodide, which is what many organic chemists would think of as a byproduct of this reaction. The other thing that you'll often see, we've done this a little bit so far, but I'm going to do this explicitly, is a solvent written below the arrow. Virtually all organic reactions are carried out in solvents. Solvents do a few things. They allow reactants to mix, they allow different species to get together, and they allow a compatible environment. So for example, in this reaction, sodium cyanide is an inorganic salt. Ethyl iodide is a liquid. Sodium cyanide doesn't dissolve in ethyl iodide. Ethyl iodide is a mildly polar organic liquid, almost non-polar. Sodium cyanide is a salt. You need very strong interactions to solvate the sodium and cyanide ions. Ethanol is a great solvent for this because ethanol is like water in some ways. It hydrogen bonds. It has strong dipoles in it, so it can stabilize cations and anions so they can dissolve. It also is miscible with most organic compounds, so it brings the two reactants together. The other thing that an organic solvent does is it allows heat to be dissipated. Most reactions that proceed, most reactions that go to the right, end up releasing heat. And as such, if you just mix two pure reactants, if the reaction becomes exothermic, if the reaction's exothermic, you may get a lot of heat very suddenly, literally potentially getting an explosion. Solvents dissipate heat. They also can boil to relieve heat through evaporation. And often a reaction in your lab course will be carried out in a flask with a reflux condenser so that solvent can be boiled to heat the reaction up, but also so that any heat can just go with the boiling solvent and the solvent can then condense with the condenser. Now, organic chemists are so organocentric that you may see the same reaction written as follows, where you simply put the organic reactant on the left-hand side of the arrow, put your reagent inorganic, organic, or organometallic compounds that participate in the reaction over the arrow, solvent under the arrow, and your organic product the right-hand side of the arrow. And all of these ways of writing this reaction are correct. Writing it with the byproduct shown, without the byproduct, writing sodium cyanide on the left of the arrow, writing sodium cyanide over the arrow. They're all just putting slightly different emphases on what we're thinking about things. Now this particular reaction falls into the class of reactions known as a substitution reaction. In the substitution reaction, one group literally replaces another. So I'm going to write this same reaction, but I'll show the bonds that we're making and breaking. So we have a bond between the ethyl group, specifically between the methylene carbon and the iodine. And we have cyanide anion. And so we substitute the bond to the iodine, we substitute the iodine with a cyano group, with a nitrile group. The other product of this reaction, specifically as I've written it, is iodide anion. So basically, cyanide comes in and it replaces, it substitutes the iodine, and now we end up with cyanide bound to the ethyl group and iodide kicked out. Cn replaces I in this reaction. So what we're doing, to be very specific, is we're breaking the sigma bond and we're forming CCN bond. Thoughts or questions? We've already seen that one of the ways we think about reactions involves the use of arrows of various sorts. And this really is integral to the language of organic chemistry, where specific arrows have specific meanings. And some of you may find, if you don't use, or have already found on your midterms, if you haven't used the correct sort of arrow, you've miscommunicated and perhaps even lost credit for it. So I want to talk a little bit explicitly about various sorts of arrows that we've been using to show reactions, to show equilibria, to show resonance, and to show bonds making and breaking. So let me write a couple of these out. So when I wrote the reaction before, I think we wrote something to the effect of CH3 CH2I plus NaCN goes to CH3 CH2CN plus NaI. So that arrow there is just specifically a reaction showing reactants to product. Doesn't say anything about whether it's an equilibrium. And that's fine. We've communicated a chemical transformation. Technically, I can say every reaction is nominally reversible. By that I mean, it's never really completely wrong to think of any reaction as an equilibrium. But in some cases, they're so energetically downhill, it's kind of silly. Let me show you an arrow we could write to indicate specifically that we were talking about a reaction that's an equilibrium. If we use this sort of arrow, this arrow implies an equilibrium. I generally write this as two regular arrows, one over the other. You'll also see this written in particularly typeset, where you have arrows like this. I think the chemical drawing program I use typically does that. Your book may do that as well. Neither one is particularly different from the other. Show you a case in just a moment where there is a big difference between an arrow with a double head on it and an arrow without. Let me show you one more variation on the arrow. Same reaction. Probably a little bit more correct for this reaction is showing that the equilibrium lies very far to the right. If you're going to say it's an equilibrium, this particular reaction would be one where you'd want to indicate, yeah, it's not an equilibrium in the middle. I'll say indicates the equilibrium lies to the right. All of those sorts of arrows on the blackboard on your left really are the sort of arrows you've seen in general chemistry. Other sorts of arrows are unique to organic chemistry, and ones that, as I've indicated on many occasions, really are central to our thinking about how bonds get made and how bonds get broken. Curved arrows show the flow of electrons. In the making and breaking of bonds. And specifically, a curved arrow with a regular double head on it shows the flow of an electron pair. And that kind of makes sense, given that all of the bonds that we've talked about involve 2 electrons for every single bond. So a double bond involves 4 electrons. In other words, bonds involve electrons in pairs. We'll say in bond making and bond breaking. And so it makes sense that your arrow has to start where the electrons are. You can't just have an arrow, a curved arrow, starting on an atom where there are no electrons. It needs to start on a lone pair or on a bond where the bond is breaking or the bond is moving. So for example, in the reaction that we're talking about here, this reaction of ethyl iodide, which we'll learn is called an SN2 displacement reaction. I would show electrons flowing from the lone pair on the nitrile to the carbon atom. This is going to represent the new bond that's being formed, this flow of electrons. And concurrently, electrons are going on to the iodine atom. And here's our new bond to the cyano group. And depending on whether I'm feeling like it, I might show all of the lone pairs on the iodine. Often, because organic molecules are big, often people only show the electrons right at the region, right at the center of the reaction, just because there's a lot of extra atoms in the molecule. But here I'm feeling good, and I will go ahead and draw everything out. And here's our iodide anion. Now, there is another class of reactions, and there are reactions that involve single electrons moving. A lot of these reactions involve free radicals, either the reactions of free radicals. A free radical is a species with one electron on it. They're reactive. You've probably heard of this term. You've heard the term radicals in aging. Okay. These are reactive species that form under a variety of conditions, including oxidation reactions from molecular oxygen and various sorts of photochemical reactions from sunlight. And these are reactive species that have a single electron to them. We use what's called a fishhook arrow to show the motion of single electrons. And by a fishhook arrow, what I mean is a curved arrow, but instead of having a double head on it, having a single head on it. So an example would be the breaking of a bond in a peroxide. The oxygen-oxygen bond is very weak, and it breaks easily, for example, with heat. So if I take a simple peroxide, this one is dimethyl peroxide, and let's say we heat it up. The delta over the arrow means heat. Just a Greek letter delta, capital delta, like you'd see on a fraternity t-shirt, often used to mean heating a reaction. So breaking the central oxygen-oxygen bond involves moving one electron onto oxygen, and so I use one fishhook, and moving the other electron from the central bond onto the other oxygen, so I use another fishhook to designate this reaction. The overall result is that we get two methoxy radicals. Each of these methoxy radicals has 7 electrons around oxygen instead of 8. one electron in the bond from one pair of electrons in the bond from oxygen to the methyl group, another two lone pairs of electrons, and then an odd electron. And the motion of that odd electron from the bond onto the oxygen atom has been shown by this fishhook, designating the breakage of that bond. When we talk about bond energetics, sometimes students get a little bit confused because there are two different energies involved in breaking bonds. One is what you traditionally think of as bond strength. That's the energy to break a bond homolytically, homo-like lytic cleavage, just as we've done here, breaking it so that one electron ends up on one atom, one on the other. That's the general strength of a bond. What students will sometimes find confusing is to look at a reaction like this, where we're having a reaction occur, and then they'll say, wait a second, I thought you said this bond is strong or this bond is weak, and it's a little bit different when you're breaking bonds with flow of two electrons versus a table of bond strengths dealing with just snapping them equally in half. All right, last arrow, and you've seen this, the double-headed arrow. These indicate resonance. So on the midterm exam, for example, you saw the use of this arrow to indicate two resonance structures of an imidazolium cation. That was, I believe, on the last problem where I asked you to draw two different structures, and I think the structure that I provided, I think I had asked you to fill in a hydrogen to show a resonance structure. So I think that the structure I provided, or almost provided, was this structure. I think you had to fill in the hydrogen and the positive charge. And then we had a double-headed arrow showing resonance, showing the resonance structure. This was the structure you were asked to provide. And of course, the double-headed arrow means that it's both at the same time. Unlike the arrows where we've seen going from reactant to product, or arrows showing flow of electrons, the double-headed arrow is simply reminding us that the imidazolium, the methyl imidazolium cation, isn't solely the structure on the left. It isn't solely the structure on the right, it's both of them, and it's both of them at the same time. We're not changing between them, we're not oscillating or vibrating between them. These are just two different pictures, neither of which is complete, and together they make up a more complete picture of the same thing. All right, let's talk about a different type of reaction, one that you're going to see. We'll talk about addition reactions. So we talked about substitution reactions. And the basic idea of an addition reaction is we're going to add something across a pi bond. In the process, we're going to break the pi bond and form two new sigma bonds. We take an alkene, like cyclohexene, and we treat it with bromine. Remember, I'm using a chemical reaction showing that we're having an organic reactant on the left, a reagent, which is also reactant, over the arrow, and a product, dibromocyclohexane. And so, of course, what we're doing in this reaction is we are breaking the pi bond. We're forming two new sigma bonds. And that's the basic nature of an addition reaction. In this particular case, so an overall addition reaction can involve many, many different types of processes. In this particular case, we're also breaking the bromine-bromine bond. Sometimes we don't even have the two groups that add to a double bond coming from the same reagent, and yet you can still recognize the basic form as an addition reaction. So later on in the class, you're going to be learning about, later on in the sequence, you're going to be learning about Grignard reagents. So let me borrow an example from your textbook, which allows you, this is actually in the current chapter, so it's a nice chance to see what we're talking about. Here's acetone, and we can treat it with a Grignard reagent. Later on, you're going to learn that the name of this reagent is called methyl magnesium bromide. It's an organometallic reagent, and it acts as a nucleophile toward the carbonyl group. Right now, though, we're just looking at the basic grammar of the reaction and not the details of the mechanism or the reagents. And so in the first step, I mean, this is literally, you will add one reagent to your acetone. Sometimes you'll add the acetone to the reagent, the flask. Then you'll add another reagent, in this case, water. And when you're done, the product of the reaction is tert-butanol. And even though this is a very different reaction than you've seen thus far, and it involves different sorts of chemistries that you've learned about, you can look at this reaction and say, oh yeah, it is an addition reaction. He said in an addition reaction, we break a pi bond. We had a pi bond to the oxygen, and that pi bond is no longer there. We've broken it. And in the product, now we have two new sigma bonds. The oxygen before was bound to two methyl groups, and here it's bound to a third methyl group, so we formed a sigma bond to a methyl group. The carbon atom was bound. And the oxygen atom before just had a double bond, and now we have a new sigma bond to a hydrogen. So even this very different sort of reaction falls into the broad class of addition reactions. Question? So right now we're taking kind of a look from 30,000 feet at a lot of what you're going to be learning over the remainder of the course and just getting a feeling for the different types of reactions. Again, in this view from 30,000 feet, one of the things that's very pretty is a lot of reactions have paired opposites. So the equal and opposite, the reverse, if you will, of an addition reaction is an elimination reaction. What do I mean by the opposite? I mean that in the case of an elimination reaction, we're going to break two sigma bonds and get a new pi bond. All right, let's take a look at an example of an elimination reaction. And indeed, this is an elimination reaction that you'll be seeing in the very next couple of chapters. So we'll take a reaction. First, I'll write it out in sort of a shorthand. And this molecule is tert-butyl bromide, also known as 2-bromo-2-methyl-propane. If we treat it with sodium ethoxide and ethanol, and now you're seeing this grammar of putting reagents over the arrow and solvents under the arrow. I've already mentioned in an earlier class how one often generates this base sodium ethoxide by throwing sodium metal into ethanol and letting it dissolve. If we do this, then the product of this reaction is an alkene, 2-methylpropene. So we can see there wasn't a pi bond in the reactant, and now we formed a pi bond. Let's look explicitly at the sigma bonds that have been broken. So I'm going to draw out our bromobutane, our tert-butyl bromide rather, large. And I'll draw our product large, and I'll draw everything explicitly. So here's the pi bond that we formed. And you can see the sigma bonds that we've broken in going from a CH3 group to a CH2 group. We've broken one of the bonds to the hydrogen. And in getting rid of the bromide, we've broken a bond to bromine. As we go on to learn about substitution and elimination reactions, we're going to be learning about species called reactive intermediates. And I've already hinted at them with radicals. Certain organic species form transiently during reactions. Generally, these are not species that you can put in a bottle. This, of course, means that organic chemists have worked very hard to figure out how to put some of these species in a bottle, because if you say there's a rule you can't do something, organic chemists want to figure out how to try and break it. However, let me show you general examples of the sort of reactive intermediates that you're going to see that in general just form transiently for a fleeting fraction of a second and then go on to a product. I'm going to draw them out explicitly because it's easy later on to get confused about the subtle distinctions between them. Carbocations are carbon-bearing reactive intermediates in which you have a positive charge on carbon, in which the carbon lacks a complete octet. We call them carbocations because they are literally cations on carbon. Let me write my A meter here. Not surprisingly, carbocations are unhappy because they lack a complete octet. And so they form transiently and then go on to carry out various reactions that give them a complete octet. In the case of the bond homolysis to form a methoxy radical, we saw another type of species, a free radical. Radicals are species where you have an odd electron on an atom, and a carbon-centered radical is simply a radical with an odd electron on carbon. Just like carbocations, they're not happy. Carbon wants a complete octet, and it does various things to get it. What's interesting is that the reactions that carbocations do to get their complete octet are different than the reactions that carbon-centered radicals do. That's not surprising because carbocations need 2 electrons, so they carry out reactions that get them 2 electrons. Carbon-centered radicals need 1 electron to complete their octet, so they carry out reactions that get 1 electron. Often those reactions involve stealing, whereas reactions of carbocations often involve sharing. Now, the last reactive intermediate is kind of a little bit different than the other two. And I'll draw it, and your textbook draws it. It's a carbanion. Carbanions have a complete octet on carbon. They're anions, negative charges centered on carbon. The carbon has a lone pair of electrons and a net negative charge. Carbanions you will rarely see as actual carbanions floating around. In general, they are simply something we will think of as an alternative structure of an organometallic reagent. But the reason carbanions in general are unhappy is carbon isn't that electronegative. So there are many things that would better stabilize that negative charge than carbon. Carbon's electronegativity is much less than, say, oxygen. So in the reaction of the Grignard reagent, where we have a carbon-magnesium bond, magnesium is electropositive, we will often think of our Grignard reagent as being like CH3 minus MgBr plus in its reactivity, hence being like a carbanion in its reactivity. And you will learn more about these species and about organolithium reagents later on. All right, let us finish up by talking about a couple of examples of reactions that are going to set the stage for things that we're talking about later on. So in our reaction of cyanide with ethyl iodide, we have no intermediate. And and I'll draw the curved arrow mechanism once again, just to make this very, very explicit. In a single process, the cyano group comes in, the cyanide group comes in, and we form a bond to carbon, and we break a bond to iodine. This is an example of a concerted process, one in which we've gone without an intermediate from a reactant to a product. Let me now show you an example of something that occurs in steps with a reactive intermediate. That reaction, by the way, is called an SN2 reaction. The reaction that I'll show you now is an example of an SN1 reaction. All right, if we take tert-butanol, if we take 2-methyl-2-propanol, and we treat it with HBr and H2O. If we treat it with hydrobromic acid, and HBr and H2O dissociates to form H3O plus and bromide anion, and those are going to be the players in this reaction. The product of the reaction is the 2-bromo, 2-methylpropane that we saw before, tert-butyl-bromide. So this is a substitution reaction, just as the other example was. We've broken a bond to oxygen, and we've formed a bond to bromine. How does this reaction occur? This reaction occurs by way of a carbocation intermediate. And you're going to be seeing this a couple of times again, so don't worry if this goes by fast today, because this particular concept is going to be coming back again and again. In the first step, we protonate the oxygen. And I'm using curved arrows to show the flow of electrons from the lone pair to the hydrogen, breaking a bond between the hydrogen and the oxygen, just like we did on the midterm exam. And now we form protonated tert-butanol. In the next step of the process, and again, don't worry if this goes by fast, because we're going to be seeing it a couple of more times. In the next step of the process, we have a protonated OH group. It can leave, taking its pair of electrons with us to give us a tert-butyl cation. Here's our reactive intermediate, the tertiary butyl carbocation. In the final step of this SN1 reaction, now our carbocation, which is unhappy because it doesn't have a complete octet of electrons, now undergoes a reaction with bromide anion, which is present in our HBr solution. Bromine, bromide, having a pair of electrons, is willing to share it, and I draw my curved arrow from the lone pair of electrons on bromide to the carbon atom, and the overall result now is the formation of the new carbon-bromine bond. All right, well, next time we're going to be picking up, continuing our theme of discussing reactions. We'll talk about the energetics of reactions, and then we'll go on later in the following lecture to talk about some reaction-free energy diagrams